So for this problem, we'll be looking specifically at information on sulfuric acid, H2SO4, if we had a specific mass and we were dissolving it to make a specific volume of solution. And the first question here wants us to determine what the concentration of our sulfuric acid is. Now concentration will be focusing on the units of molarity, which will always be defined as the number of moles of our solute, or what's being dissolved, divided by the volume in liters of our total solution. And sometimes you will see the notation of a bracket to indicate molarity as well. So whenever we talk about concentration, you might see, rather than concentration of H2SO4, you might see a bracket. But the first thing that we need to determine is what the number of moles of our sulfuric acid are, and we start with 1.25 grams of H2SO4. And if I was to go to my periodic table, I can go through and find the molar mass of 2 hydrogens, 1 sulfur, and 4 oxygens, and then I'll come up to be 98.078 grams for every 1 mole of our H2SO4. So my number of moles here are going to be 0.012745 moles. And since I started with a mass of 3 significant figures, I want to keep those 3 sig figs in my number of moles. And since I'm working with a volume of 10 milliliters, I'm going to need to convert my 10 milliliters to liters. So for every 1 liter, I will have 1,000 milliliters, which will give me a value of 0.0100 liters. And this is important because I had 3 sig figs for our number of milliliters, 10.0, that's 3 sig figs. So our volume in liters needs to be 3 significant figures. And remember that as long as we have a decimal place, all trailing zeros are significant, not the leading zeros. So the 0.0 at the beginning is not significant. The 100 are our 3 sig figs. So our concentration of H2SO4 will be 0.012745 moles, again to 3 sig figs, divided by 0.0100 liters, and I will get a value of 1.2745 molar to 3 sig figs. So my answer here is going to be 1.27 molar. Now, one thing I would like to point out is that whenever we're working with multi-step problems, you always want to use the rounded value as the answer, but never use the rounded value in continued work. So even though my answer here is 1.27, I should still continue to use the 1.2745 in my calculations. Now, this is information about sulfuric acid, but sulfuric acid is considered to be a strong acid, which means it fully deprotonates in water. So if you were to have a container of sulfuric acid, what you would actually have is a container of water with a lot of protons and a lot of the sulfate ions. So for the next part of our question, we want to look at the concentration of the individual components. So if I was to take my sulfuric acid and it is aqueous, that means it's going to break up into my proton ions and my sulfate ions. Both of them are going to be aqueous. So if I balance this out, I'll have 2 protons for every 1 sulfate in order to make my sulfuric acid. And from this, since I know what my number of moles are from my original calculation, I know what my concentrations are, I now know my individual concentrations here. Since it's all the same volume, I can treat my molarity and my number of moles very similarly. So for 1.2745 molar of H2SO4, I can convert that by saying for every 1 mole of my H2SO4, I will have 2 moles of my protons, which would mean I would have a concentration of 2.5490 molar of our H positive protons. To 3 significant figures means I'm going to have a concentration of 2.55 molar. And then if I do the exact same thing, 1.2745 molar of our sulfuric acid, and we do this for our sulfate ions, it's just going to be a 1-to-1 ratio. Which again will just be 1.2745 molar of our sulfate ions. So that is going to be 1.27 molar. So we have our breakdown for the concentration of our overall ions and our overall compound. And we can take one step further by saying to what volume would we need to dilute the solution in order to obtain a concentration of our sulfuric acid at 0.100 molar. So whenever I see the word dilute, there is a specific formula that we must remember. It's all based on the fact that the number of moles in our dilute solution are equal to the number of moles of our concentrated. The number of moles will not change. It's as if I was to take this cup of coffee here, and if I was to pour a lot of water in here, the number of moles of coffee or whatever substance I have, the number of moles are never going to change. The only thing that's going to change is the total volume of that solution. So since my number of moles of diluted and concentrated will be the same, I can take this one step further because I know that my molarity is always moles over volume. So my molarity of the diluted times the volume of diluted will always equal the molarity of the concentrated times the volume of the concentrated. So let's take a look here. I know that I'm diluting the solution to a specific concentration, which means I know what M sub D is, and that all previous information about sulfuric acid will be sub C values. So I'm technically solving for volume D, which will be volume C times concentrated solution over our diluted solution, molarities. So I'm going to have a volume of our initial of 0.0100 liters. Our molarity of our concentrated, which we found to be 1.2745 molar. Divide that by our new concentration of 0.100 molar. And when I plug this in, I'm going to get a volume of diluted as 127.45 milliliters. However, and this is going to be to 3 significant figures because everything here is in 3 sig figs. This is also going to be the same thing as 0.12745 liters, also to 3 significant figures. And since they didn't really specify what units to use, you can use either or. So the volume of diluted will be 0.127 liters, which is equal to 127 point liters. And I want to be very consistent with the way that I use my significant figures and my decimal points. So you don't have to put a decimal point behind the 7, but for best practices, I will always put that just so we consistently know how many sig figs to work. Now, if we were to continue on with this problem, we have another part here that talks about writing the balanced complete ionic and net ionic equations for a reaction with our sulfuric acid as well as our potassium hydroxide. So using this information, we can go through and use our solubility chart with hydroxide and potassium. And we know that anytime that you have a potassium hydroxide solution, it will be insoluble. However, we want to deal with an acid-base reaction, so we're going to actually be working with a aqueous solution of our potassium hydroxide. So it's as if someone had taken a potassium hydroxide tablet, put it in water, and allowed it to dissolve. So we're dealing with an H2SO4 aqueous solution plus our potassium hydroxide solution. I'm going to break these up into our ions to work with. So we have our protons, we have our sulfate ions, we have our potassium ions, and we have our hydroxide ions. And since this is a net ionic equation, we are going to reshuffle our ions. So our products are going to be our H positive with our OH negative, and then our potassium with our sulfate. So our products should be HOH and K2SO4. Now, some people don't really look at water as H2H, HOH, they look at it as H2O, but H2O and HOH are actually the exact same thing. So one of the tricks and tips that I always tell people that whenever we're dealing with acid-base reactions, I would suggest leaving water as HOH, because HOH and H2O are legitimately the same thing. The difference here is you recognize where does the proton and the acid and the hydroxide from the base go. It's just another way of looking at things. And when I go through and I determine my solubility, my water is always going to be a liquid. But when I look to sulfates, if I look at my solubility table here, I know that my sulfate ions are always soluble, and the exceptions do not list potassium. So my potassium sulfate will actually be an aqueous solution. And now I need to go through and balance. I have 2 protons in my sulfate, which means I would need 2 protons in my water and listed as HOH. I would therefore need 2 hydroxides in my potassium hydroxide, And finally, I would need 2 potassiums in my potassium sulfate to balance out with the left. So my final overall balanced equation is going to be H2SO4 aqueous plus 2 potassium hydroxide, so aqueous solutions, and it's aqueous because it is specifically an acid-base reaction. We're going to have 2 waters, which I will list as H2O for those of you who do not like HOH, and I will have 1 mole of our K2SO4 aqueous salt. So this is our complete ionic equation. But this is our complete. Now we need to work on our net ionic. And for our net ionic, we take anything that can be separable into separate ions. Everything but the water can be separated. So when I separate all my ions, I'll have 2 protons from our sulfuric acid. I'll have our 1 sulfate ion from our sulfuric acid. I will have 2 potassium ions from our potassium hydroxide, and I'll have 2 hydroxide ions from our potassium hydroxide. And since everything on the left-hand side was aqueous, all of those ions will have to have that the aqueous designator on every ion. I'm going to yield 2 waters, H2O liquids, because since it's in a liquid form, it's not aqueous, it's liquid, it's not separable. And my potassium sulfate will be separable. 2 potassium ions and 1 sulfate ion. And what you're going to see here is that my potassium and my sulfate ions exist as ions on both sides. So those are our spectator ions, and our spectator ions are going to cancel, leaving us with 2 protons and 2 hydroxides yielding 2 waters. So 2 protons that are aqueous plus 2 hydroxides that are aqueous will yield 2 waters. But this is not balanced. This is a ratio of 2 to 2 to 2. If I divide everything by 2, I'm going to get everything boiled down to 1. So my net ionic equation for this strong acid, strong base solution will be 1 proton plus 1 hydroxide will yield 1 water. Now there's a nice little cheat to this, because if you know that you have a strong acid and you know that you're mixing it with a strong base, you will always have a net ionic equation listed here. Repeat, if you know that you're mixing a strong acid with a strong base, this will always be the net ionic equation. Now from this, we can work with determining information about our titration. And in this question it states, in a titration, how many milliliters of a concentration of potassium hydroxide would be required to get to a neutral endpoint for our original solution? Now, our original solution here was given a concentration value, so H2SO4 was given a concentration of 1.2745 molar. Now, the important piece of information here is our neutral endpoint. Because for a lot of people, they say the moles of acid equal the moles of base. And that is not true. I know, right? It's not the moles of acid equal the moles of base. That's just a shortened way, an easier way to remembering it. For a neutral endpoint, the proper definition is that the number of moles of protons are equivalent to the number of moles of hydroxides. Now, I'm sure that you're sitting there looking at it going, well, isn't that the same thing? Isn't moles of acid the same as the number of moles of protons? Not if you remember Part B from the work that we did originally. Because our Part B concentration, a number of moles of H2SO4, were not the same thing as the number of protons. We have to pay attention to acids and bases that give up more than 1 proton or more than 1 hydroxide. So this is a really good question because it forces people to remember that the number of moles of acid doesn't necessarily mean the number of moles of protons. But I already know the number of moles of protons. I found that earlier in Part B. So the number of moles of protons that I had was 0.025490 moles. I found that earlier. But now I can also say that this is equal to the number of moles of hydroxides. If I was to reach that neutral endpoint, all of the protons must react with a maximum amount of hydroxides, and that's the number of hydroxides. So by knowing how many moles of protons that we had earlier, we now know how many moles of our hydroxides we have. And we can convert the number of moles of hydroxides to the number of moles of potassium hydroxides, because I know that the number of moles of potassium hydroxide is equivalent to the number of moles of hydroxide, because KOH breaks up into one potassium and one hydroxide. So the number of moles of KOH will always be the number of moles of our potassium hydroxide, since it's 1 to 1. So this also equals the moles of KOH. So finally, I can say that my concentration is equal to the number of moles of our KOH divided by the volume in liters. So our volume in liters will equal the number of moles of our KOH divided by our molarity of KOH. So 0.025490 moles. Divide that by our molarity given of 0.250 molar, and this will give us a value of 0.10196 liters to 3 significant figures. But the answer was asking us for the volume in milliliters, so I can convert this and get my answer. My volume of our titration, or in this case our base, will equal 102 milliliters. 3 significant figures converted to milliliters. So the key to this is recognizing both how you're going to break up an acid or a base into its component parts. We're constantly remembering how to work with the number of moles and molarity, working with a complete ionic equation, and how to break that up into a net ionic equation, and then what a proper definition for a neutral endpoint is.